Okay, in my history of terrible analogies, I think that we need to continue with the terrible analogies and go a little bit. Nope, we're not doing the children anymore. As a matter of fact, the hill is just a hill. The hill is a hill now. It's not made of children. Okay, it's just a normal earthy hill. All right, so it's a normal hill. Okay, a normal hill that water is specifically flowing down. In this analogy, a battery represents voltage, or how much energy you are potentially going to give. Okay, um, the current would be the flow of water in this particular case. So you could, of course, get more current simply by increasing the size of the hill. What we ended with yesterday is that resistance, and this is an important understanding. Despite the word resistance, resistance is not an actual thing, it's a mathematical ratio. Okay? Resistance is the same as velocity. Okay? Velocity is what? It's just a ratio between distance, displacement, and time. That's it. Resistance is just a ratio between voltage and current. Okay, so one of the best pictorial demonstrations of this is, where's media? Media, circuits. Where are you at, circuits? Are you not on here? Where did I put you? Ooh, I might have put you in backgrounds. Hold on. General. Backgrounds. Go to physics. Where's that? It's got to be here. Come on. Yeah. Oh, it's here. There you go. There's a basic circuit. Volt is the push. Resistance is the thing that is keeping it specifically from going, of which there are several reasons that it could. And amperage is how much current is actually getting through that particular system. Okay. The units of a volt are really a what? Joules per coulomb. Again, understanding what a unit actually is, it can be very helpful. An amp is actually a coulomb per second, and an ohm is actually a volt per amp. Correct. How many volts you get per amp. So like I said yesterday, if you see something has 100 ohms, what you're seeing is that it actually has 100 volts for every 1 amp. And we believe, which we'll talk about here in just a second, we believe that it's a direct relationship. What if it's not? Well, we will talk about that here in just a second. But to pull this up, this will be a little bit more obvious next chapter. But resistance is futile in this particular case. We'll talk about why then. Yes?
Does a higher or lower resistance mean like more resistance?
Exactly what you would expect. Exactly what you resistance. More of it is more resistance. 100%. So essentially, you look at that ratio that I just said a second ago. Okay, it's the reason why I'm not afraid of you getting hit by the Wimshurst machine, but I am afraid of you getting hit by the outlet that's right over there. Okay, you get hit by the Wimshurst machine, you're getting hit by something like 40,000 volts. Why am I not worried about it?
Not much charge.
Why?
Charges.
Why? What does that electricity have to pass through?
Yeah.
Most importantly, the air. And is it easy to get through air?
No.
So which would mean the resistance of air is incredibly high. Something on the order, if my skin is 100,000, I'm just making something up. I don't know exactly what it is. But, well, actually, we can straight up look it up rather than just make a guess. But resistance of air, I would imagine, is going to be, well, we actually calculate this later, but let's just do this. Resistance of air. No, not air resistance, you dummy.
You don't have to say electricity.
What?
The resistance of. Oh, never mind.
So somewhere on the order of times 10 to the 10th or 10 to the 14th ohms per meter. So per centimeter is probably more appropriate, but that still brings us down to like times 10 to the 8th in that particular case. So if you have basic calculation here, not specific numbers, but if I have something on the order of times 10 to the 4th volts divided 10 to the 8th, oops, screw this up. Actually, no, I didn't screw this up. Current is equal to delta V over R. So 10 to, I'm just going here, 10 to ohms, how much current are we putting out? Times 10 to the -4th. Current is actually running through that particular system, which I'm not super worried about. Yes?
When we say air, like what is air? Like air, like when you when you breathe out, like you're like.
Don't just assume you're asking a bad question and laugh.
Like you're breathing out carbon dioxide. Like is air just a mixture of every thing? Like but then like all of them have different resistivities. So like is that like?
Yeah, that's true.
Just
But
a
the
mix?
percentage of how much nitrogen's in the air, how much oxygen's in the air, how much hydrogen's in the air is pretty darn consistent with as much as we have of each. So even though you're right, they all have these different resistances that are in there, you can average it out when you have that many of a particular type pretty easily and get a pretty darn close resistance of air. That being said, as you saw up here, there's obviously some stuff that changes this because the thing said a second ago that the range on the resistivity of air is pretty darn high, stretching from times 10 to the 10th to 10 to the 14th. Means that's separated by what? At least 10,000 of something. So there's probably some other factors which we'll discuss here in just a second.
Okay.
Aiden.
Well, I mean, my question was tapped into by that because
Okay.
I didn't see initially that it said temperature affects it. I was going to ask if it did.
Yes.
What else would affect?
Yeah, we'll get into that absolutely here in just a second. That is one of the goals, a few of smaller goals for today. The big goal that I want you to get out of the chapter is honestly just kind of a general picture of a circuit. So that's why I actually started with this, and I should have kept going. So the resistance in this case is kind of hard to explain, but we could kind of think about the resistance of this as the stuff, the rocks inside the stream / the size of the stream itself / some other factors. But I'm going to digress on that analogy due to the fact that I'm really going to try to be doing a crappy analogy for what is actually the things that affect resistance here in just a second. So we'll talk about what affects resistance, but again, I'm going to reiterate, resistance is really just a mathematical ratio between the two. Now, there are things, if you had to say what you thought would control resistance, what would you say? I would say that's not the first one that you probably should say. Material. 100% material, because several of you pointed it out the other day when I asked what's the case of that ratio being high or that ratio being low, and several of you pointed to vocab that we used a minute ago. What vocab did you use? Conductor and insulator, right. Now what we find is that the terms conductor and insulator are vastly more gradient than just it either does conduct electricity or it doesn't. This number right here tells you exactly how good it is at conducting electricity, or arguably anywhere in between, right? Can you get electricity through air?
Yeah.
Yes. Is it very challenging to do?
Yeah.
Yes. So that ratio for air is ridiculously high because you can get current, but it's going to take a whole crap ton of voltage. Why is this considered a conductor? No. Very low resistance. Why? Because you can get current, and do you have to try that hard? No. That being said, one thing you might not think about is that metal does in fact still have a resistance. It does actually keep electricity from flowing through, which we'll talk about in just a second. So voltage, current, resistance is how tight it is, or if you like, voltage, resistance, current traveling through that particular guy. Voltage is how much energy, how much push, how much oomph, right? Current is like a flow of water, except it's not a flow of water, it's a flow of charge, right? Is it an actual, is it a velocity? Nope. What is true of the velocity of current? Very, very slow. How can we have such a slow velocity and still pull off a huge current? a lot of charge jam-packed in there, a lot of charge density in that conversation yesterday. So we said at the beginning of this that our ultimate purpose is controlling energy. How much energy goes where? So what you can think of with the resistor is if I know that a resistor has 100 ohms, okay, aka 100 volts per amp, I can use that to control how much current is flowing through my system. Essentially, increasing the resistance is like taking it and squeezing it, so what should happen to the current? The current should slow down, I'll get less energy in that particular case, okay? Or more if I go vice versa. So the whole purpose of a circuit is to control those two things. Because we discussed yesterday that this is joules per coulomb, or, sorry, I'll go back to it for just a second, joules per kid. Okay? And if I want energy, I've got to have children, or kids, roll down the hill. If I want to know energy over time, I need kids per second. So joules per coulomb, children per second, gives us joules per second, aka power. To give you yet another analogy, imagine we were a set of bullies, okay? Obviously look at our physical appearance and our deformed structure of society and how it actually works. And we decided we're gonna steal money from every kid that passes through. Now, in this particular analogy, we're gonna assume that every child passing through has the same amount of lunch money, okay? So every child has, say, there's $10 per child. That's its voltage. Another way to think of voltage is that's the ratio of how much energy per charge, or a charge carrier carries this much energy, or a child carries this much money, right? So if we set up a barrier right out here, okay? We set up a barrier right up here and we want to get more money, okay? We could do a couple of things. First thing we could do is we could ask for more money per kid, aka more voltage. Okay? In this case, we can use less children and we could get a large amount of money. Yes? Or we could ask a relatively low amount of money. In this particular case, we could only ask, a small amount, in which case we'd probably get a better flow through our particular hallway, increasing the number of children per second. So if I want to know how much money I get per second, I need to know how much money per child, right? How much energy per child, and I need to measure out here how many kids per second. If you want current in terms of like kids in the hallway, when the bell rang, I would stand here and I would go 1, 2, 3, 4, 5, 6. I could count all the kids passing by one spot, okay? One spot right here, divide by the amount of time, and that would tell me children per second, or the amount of current. How are we doing with this analogy thing? Doing good? All right, let's move on. So the purpose of a resistor is really to control current so that you can control energy in this particular case. All right. I think we have like 3 things and I'm done. I believe it's 3-ish. Talked about that, we'll talk about that later. Okay. So, let's talk about the lab that you're going to do in a second, okay? And talk about how we measure anything. Resistance is just a ratio. So if I said to you, okay, using this basic circuit, assuming that you can control things, okay, how could we measure the resistance of a material? What would you need to do? What's that? What you got?
Measure voltage.
Measure voltage is one thing. And what else would we measure? Current. If I were to measure voltage and current, what would you do then?
Divide.
You probably, well, hold on. Because what do we have to be careful with in a lab setting? Why can't I just take those two numbers and divide it?
Oh, you have to figure it out.
The problem with that is let's look at that on a graph, what you just did. Which side do you want to be which? Where do you want to put what?
I on the
Voltage
Y.
on the Y.
Voltage on the Y. Absolutely. How come?
Because it's on the Y.
This is already on the Y up there, so might as well keep it on the Y. Okay, and therefore the X should be
Current.
current. What's the problem in doing? This is important for what Jaden just said. He just said, let's get two numbers, let's divide them.
Air.
Sure, let's assume it's perfect.
Well, then you
Even
won't
if
have
it's
a Y
perfect.
variable.
What's that?
Then you don't have a Y.
No, we would a Y variable. You measure delta V, you measure current. What'd you find?
That's.
You got this.
Yeah.
It's not.
What's the problem?
It's not a graph.
We don't know. You don't know it's constant. You don't know it's going to stay exactly the same. Right? What if this is the graph? Yes, 100%. It's over. That does not work. Okay? Now, ideally it's not. So why do we have to make multiple measurements? Because we don't know what the relationship is. Our hope is that the relationship between voltage and current is linear. And if we make a multiple set of measurements, okay, we might get this. Oops. In which case the resistance is going to be specifically what?
Linear slope.
Slope. Thank you. The slope of this particular graph will be resistance, and it's linear, and we're good. But here is the thing. If it is linear, okay, a resistor is said to be ohmic. AKA, what it essentially means is it follows this law. It's linear, it follows that law. Here's the problem. Generally, all resistors that we have, let me actually get out some resistors so you see what the heck I'm talking about. Literally everything has resistance. So when I say when I say a resistor, it is a specific material that is in fact ohmic. But here's the truth. With the factors we are going to talk about in a second, you've probably seen these if you've ever. Don't worry. They're right, Chief. There they go.
Uh-oh. What's your name?
Hey.
It's
What did you do?
This is very slimy.
It is.
You already passed on.
He's contacting us from the grade.
Yeah, okay, so all of these right down here are resistors. The thing about them being ohmic is we can predict them. But here's the thing about all type of things. They are only ohmic within a particular range. Because here's the problem. What happens as that graph, as current goes up and up and up and up and up? Well, we've also got more voltage. So that means the hill's getting higher and higher, and I'm flowing more water through. So what's the major issue here?
That's a lot.
A lot of what? Energy. And what is that? Where does extra energy go?
Heat.
Heat.
That's not good.
Chemistry, people.
That's
Too much
fire.
heat in a particular area or a material is probably going to cause a
Melt.
chemical reaction.
Yeah.
Chemical reactions are potentially then going to change the material, and therefore, is that going to work operating outside the correct parameters? No. So, truth be told, every single material is actually non-ohmic if you go far enough. Most of the time, what it actually is with the material is it looks something like this. So what we do is we say, hey, here's your range. Within that range, the material is ohmic. Beyond that range, well, don't do it beyond that range. You're going to get too much energy and it's going to break. Which brings me to actually a very important thing to talk about with circuits, kind of three generalized terms that are going to be very helpful. I'm going to put in here three elements: a battery, a resistor that you've seen before. Notice, by the way, I've said this before, a resistor is just a light bulb without the thing around it. Okay? And then I'm going to put in there a switch. Now, the problem with a switch, this is an open switch, and thus this thing is known as a open circuit. Open circuits aren't inherently bad. The issue is when it's open, What's actually between those two? Air. As you said earlier, air has a resistance of something like times 10 to the 8 per centimeter. So with this guy only being 1.5 volts or something like that, or even any reasonable amount, even 120, even my 40,000, guess how much current's coming through that spot?
Not very
None.
much.
Zero. There is no current that is actually going through this system. It's kind of like having a set of tubes, and nope, the tube is entirely blocked off at this particular point right here. So, open circuit. Now we get to what would probably make sense here, what we really want, a closed circuit. Notice in both the closed circuit and open circuit, I have a resistor. And then I will draw a very important thing. Some of you actually created it the other day. It was no big deal. Somewhat. We'll talk about why in just a second. It was no big deal. But if I use the term, I'm pretty sure all of you know it is a bad thing. This is known as a short circuit. The defining characteristic you can see in its picture. What's the defining characteristic of a short circuit? There's no what? There's no resistance. Why is that a problem? No resistance means, hey, electricity can flow. We're good. We're great. What's the problem? Extra current is not inherently a good thing. A lot of extra current means
Is that why
a
we
lot
do
of extra energy. And a lot of extra energy means heat.
Yeah, it
And
kept
heat,
burning me.
of course, could be bad for I would say about 3 reasons, but let's just start with the easiest. Okay, the easiest thing is if there's too much heat, especially in a small wire, that wire is going to melt. And if that wire melts, no, not quite. Boom, the wire just melted. What's the issue? It's an open circuit. And the problem with that happening to, say, an iPhone is that those circuits are so ridiculously complicated in there. Would it make sense for you as Apple to hire somebody to go find exactly where that thing is and fix it? No, probably. It actually makes much more sense economically for you as Apple to just straight up replace the phone, because it would take vastly more time and energy to go find out where that short circuit is. The thing is, if there's a short circuit and there is your electronics working anymore? No. So too much current. The first bad thing about too much current is death to electronics. Death to electronics. Also, coincidentally, that's my college band's name. All right, death to electronics. Now, the other bad thing about a short circuit is, let's say it happens in a home because of faulty wiring. Faulty wiring basically means you've created a short circuit, you've done something that's not the code, you've basically done something that you've allowed too much current to go in a particular area, and there's absolutely nothing stopping it. What's the problem with too much temperature in that case? Connected to a particular spot, that's literally known as an electrical fire, right? So too much electricity in a particular spot is, of course, bad because of fire. Okay, and then the probably most important thing about a short circuit and too much current is that your muscles run on electricity, every single stinking one of them. And most importantly is the muscle at the, pun intended here, heart of you, that runs on electricity. And that little guy right there beeps because of 0.15 milliamps, or 150 milliamps, or sorry, not 0.15 milliamps, 0.15 amps, 150 milliamps, which is why if you are near water, which would reduce your resistance of your skin and potentially put you at danger, right now code says you have to have those outlets. Notice the outlets right next to human beings in their labs are always the little one with the button right in the middle. That's GFCIs. GFCIs, yep. I always get the letters in the wrong order. So ground fault circuit interrupters, and basically what those do is those are tiny circuit breakers, and those things kick off the moment 0.15 amps cross a problem, because you're potentially around, and if 0.15 amps is going through them, it could also go through you and kill you, which is why they kick off. Good news is you can easily kick them right back on by pressing the reset button to make sure that that is the case. So, bad things about too much current coming from short circuits are: 1, death; 2, fire; Okay, so house death. All right, and finally, death to electronics. Okay, I'm trying to make this more metal than it actually is. It's a scary thing. Here's the thing about electricity. You should be. It's hard for me to balance as a teacher. You should be correctly terrified of electricity. Okay, not inappropriately terrified. I don't want to terrify anybody, but I know that I'm dealing with 13 individuals in here, and some of you in here are a little bit pyromaniacs, and you want to set stuff on fire, you want to explode things, and electricity needs to flow, and let's go! Okay? You need to be more scared. 100%, you need to be a little more scared, or you're going to end up number one. All right, so, some of the rest of you, don't freak out. We just need to manage it correctly. It's like anything that is dangerous. If handled with appropriate technique and care, it's going to be completely fine. I would argue that firearms are completely safe to someone that has learned the actual technique of going into them. But we can move on past that particular information a little bit later. So, open circuit, short circuit, closed circuit. We've talked about those. We talked about this guy right here. Okay. So this is Ohm's law. If it follows, when is it Ohm's law?
When it's linear.
What is linear?
When the relationship between current and voltage is.
And if I have a resistor, it's fair to assume that they are in fact ohmic for a particular current. As a matter of fact, if you get a bag of resistors, it'll say this is the resistance for this particular current range. Don't go outside this particular current range. And when we do the lab tomorrow, I will show you what happens if we go outside that particular current range. Okay, it's not the end of the world. Like I said, as long as you handle it safely.
So wait, all resistors are ohmic?
All resistors are non-ohmic if you look far enough. Okay,
But, like,
but it's like this. It's here. I'll show you real quick. Okay, so I hate that they did it this particular way. I don't know why they did it this way, but they switched V and I, making their math more complicated, which essentially just takes it, V equals IR. By the way, this is usually how you see it, not R equals V over I. So in this particular case, if you go I, you just put that underneath, and it's I equals 1 over R times delta V, the inverse of rate resistance. Okay, so in this particular case, what are we doing? Well, if we get more voltage, we absolutely should get more current. And this just says if we get more voltage, the current is going to get even bigger faster, which perfectly makes sense. It's weird to see this, though. Actually, no. That's actually incorrect, what I just said, because it's the inverse. So actually, the slope here is going up. So what does that mean about resistance? Resistance is actually decreasing. This is not the typical thing that you would see happen in this case. But to the point that I just said, you don't see any scales up here. Right? This might be that right there. If you zoom in on any mathematical relationship enough, it's linear. Right? Is it actually linear? Well, there's a whole conversation about estimation and the whatnot. Yes?
Is like resistance anything set? Is it? Or
No, and that's what we're going to talk about next. No. Resistance is, again, that's why I keep hitting on that sentence of resistance is a mathematical ratio between the two. You can change those mathematical relationships between the two one of a few ways, which we'll discuss actually now. I'm not going to worry about this guy because I got to get through this stuff. We talked about this. All right, perfect. Okay. I don't like the way they present it. I'm going to present it on my own. All right. So here's what we're going to do to talk about what things can affect resistance. To understand this, again, remember that a wire does in fact have resistance. So let's talk about why. So imagine a wire. Imagine this wire blown up as though it's like the size of a hallway. Now, the thing where people screw up when they imagine this picture is they imagine an empty hallway. The wire is there because it's full of stuff, right? This hallway is not empty. This hallway is jam-packed full of charge. Yes, that's why it is the size that it is. Now, you can kind of use the hallway analogy if you imagine, all right, here we go. So imagine we go to this hallway and we jam-pack it from left to right, top, ceiling to floor, full of freshmen. All right? And someone at the end of the hallway, actually, no, not at the end of the hallway, someone right here tries to count how many freshmen pass by per second. All right. Now, assuming you have full sci-fi control of that hallway and the ability to change it, what could you change about the hallway to change how many children per second, assuming that they're getting the same push and voltage the whole time?
Make the
Wider
hallway.
hallway.
You can make the hallway bigger. Okay, so in terms of, if you look at it like this, you could literally add cross-sectional area. Why does that work? Careful, that's not quite right. Because remember, this is what I meant when I said a second ago, people try to imagine an empty hallway. It's not an empty hallway. If I want to add more area, you add more children. You add more things packed into that area. Now it still works, even at the exact same speed. Okay, even at the exact same speed passing through, more area will have more children per second, because simply there are that many more children. Yes? So if I have, like, say, in this initial hallway, 9 children, and I increase it by 33%, I've added 3 kids, I've increased current by 33%. So increasing area does what then to resistance? Well, I haven't changed voltage, right? I haven't changed voltage. What did we change? Current. But resistance is the ratio from voltage to current. And therefore, if current just increased while that stayed the same, then resistance arguably just decreased. This is what I mean when I say it's a mathematical ratio between the two. With resistance, you kind of think about it as how well we're holding on to the kids. Did they change how well we held on to the kids? No, they're going the exact same speed. They're pushed the exact same way. All right, next. What else could we possibly change? Here's number 1. There's 4 factors.
Are you allowed to change?
Material. Material is easy, okay? Whatever material it is has some effect on resistance. And if you have to guess, if we don't know the effect, what do we always do?
Wow.
Make a constant. We make a constant. The constant in this case, I'll just put it over to the side, I'll show you in a second, is known as resistivity. And use the exact same, sadly, rho that we use for density.
I was doing that last night, and I was like, "What is rho? Where are they getting this?"
Rho is
number?"
resistivity.
It was making me mad.
Next. You mentioned one earlier.
Temperature.
Now, I will talk about why in later, but I'm going to let you kind of just make your general guess based on your experiences right now. As temperature goes up, what would you expect to happen to resistance?
Goes up.
Goes up.
Because if you have a higher temperature, then that means there's your children are moving faster, so there's more.
Electrons are also
So
You're close. You're not too far away. You're not too far. There's one detail at the very end that I'm going to change, but it goes hand in hand with the other factor, which is why I'm just not talking about it quite yet, but we'll tackle both of these two together. The last one, which hand in hand goes with what you just said, is the length of the wire. As the length of the wire or any material goes up, what would you expect to happen to resistance? Goes up. Now, as Aiden was just mentioning a second ago, there is a really important relationship. It's basically this, and it kind of explains why, we'll leave that actually up here, right over here. It explains why power companies don't put insulators on their power cables going that are up in the sky. Okay, and it's simply this. Remember, if this is a wire, just a bare wire that has no insulation on it whatsoever, it's not actually solid. It's made of a bunch of electrons. And as Aiden was suggesting, okay, these are bouncing around all over the place. Now, the issue is, okay, if they only ever hit each other, there'd be no loss of energy. All the energy would stay within them, except what's inherently the problem. Well, these electrons in the wire, if they are surrounded by an insulator, are going to inherently run into the insulator. Right? It's probably not going to move much, but that means what happened to some of the energy? What happened to some of the speed then? Therefore, if the speed decreases, what's going to happen to the current? The current is going to decrease. And if current decreases in this ratio, what would you say technically happens to resistance? And I say technically because, again, resistance sort of implies that it's how well the stuff is held. It's not actually how well it's held. It's just losing current because it's losing energy to other places. Then you talk about temperature. Why will temperature do that? Well, if these things are going a lot faster, are they going to make a lot more collisions with the outside stuff? Yes. And therefore, you're going to lose that much more energy. As a matter of fact, if you had a wire and you just put a battery on one end, it would not take that much time. It would take a surprisingly small amount of wire before resistance is basically so big that there's no movement of charge whatsoever. The way the power company fixes this for themselves is, one, like I said before, they don't put insulators on the outside. Number two, they have step-up stations, which basically are the power company is pushing them back and forth. They're trying to create this gigantic hill that you can kind of think about and run it down. Okay, we're losing, and then you get to a substation and boom, jump it back up so it can go further. And lastly, and probably most importantly, is the fact that all current in power lines runs on AC, not DC. DC basically means these go that way and don't stop. Well, 100% they stop because they're going to run out of energy, like I said, and that's hard to do, is push and push and push and push and push forever. Plus the fact if you did that, eventually there'd be parts of the wire that have actually worn down over time from losing too much charge and that type of thing. So instead, you simply switch to AC, where you run them back and forth. And if you run them back and forth, what is the net velocity? Zero. So technically, then what's the net length? Zero. Now, it's not perfect. You are still going to lose some energy to the outside, but not nearly as much in this particular case. All right, so we got our four factors. Let's make an equation. Resistance. Resistance is what?
A mathematical ratio between voltage.
Yeah. There we go. Voltage and current. But it's also affected by these things right here. So don't forget, the reason I highlight this is you can always replace resistance with this. So if I say, hey, go find the resistance, let's get out the voltmeter, let's get out the ammeter, let's measure these two things, boom, we've got resistance immediately. Now we don't know if it's ohmic, but who the heck cares, because we still have at least the dot on the graph of the resistance at that particular point in time. Now, first thing is, let's knock out material. Where I keep talking about resistance makes you feel like it's how much it holds, that's what material 100% actually does. Material, how well does it hold on? You can absolutely get up into those chemistry conversations of electronegativity and how well different individuals and the sea of electrons in the math and blah, 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 blah. But the point is, it doesn't matter. Guess what the resistivity of this is compared to air? Air's greater, right? You knew this. You knew this intrinsically. It's hard to get current through here. It's easy to get current through here. So resistivity should be very low for this, should be very high for this. This just allows us to measure a specific. So let's put resistivity up here. Boom, resistivity. And like makes sense, that number is very low, therefore resistance would be low for metal, and very high, thus very high for air. All right, now, let's just put all the rest of these up here in basic mathematical, just modeling fashion. More area means less resistance. So where do we put it? On the bottom. More length means more resistance. Therefore, on the top. This is where they stop, usually in the equation. I'll actually switch over to the notes now. Notice I haven't covered 4. I definitely will. So there you go. There's resistivities. The resistivities for various metals. As you would expect, glass doesn't let current, so it's got a very, very high resistivity. Okay? I thought air was on here. Maybe it's not, because it's all over the place. Iron. Iron is at times 10 to the negative 8, as you would expect. As a matter of fact, all of these metals at the top right here are at times 10 to the negative 8. Carbon actually can be a decent wire relative to air, not relative to other metals. It's times 10 to the negative 5th, which is not bad, but it's 1,000th as good as the others, so let's definitely use the others if we get the chance. Okay? So there's the equation that we just made a second ago, and we already discussed the reasons why. So if I wanted you to calculate the resistivity of a material, what would you do? You'd probably go find resistance. You'd measure the length. You'd measure the area. And then we would just graph once again, trying to get a slope for the resistivity in that particular case. I'd probably move I over here, and I'd measure delta V, and I'd measure I. Knowing those values, that would be your slope, blah, blah, blah. You get the whole picture. Now, temperature affects the resistivity, arguably. Okay? This is why you've actually seen something very similar to this equation in the past. It was the length contraction. It was length equals L0 times 1 plus alpha change in temperature. Yeah, it's just the literal same effect that temperature has on resistivity as well. The resistivity is equal to the original resistivity times 1 plus alpha, where alpha is a constant that you actually saw on the previous page. Alpha is this, the temperature coefficient of resistivity. So if you would like, with the way that you can think about that is, instead of making a new equation, what you could do is you could say, well, hold on, how am I going to do this? Yeah, so you could basically say that whereas resistance is equal to rho L over A, this is actually rho initial. So, is that rho initial? No, that's actual rho. My apologies. That's actually rho. So this should be, darn it. This is not as good as the other one. So this is just resistance is equal to rho initial times L over A times that whole mess. Times 1 plus alpha delta. I'll try this again over here. Resistance is equal to rho L over A times 1 plus alpha delta T. Oh, they just did the same thing I did. My apologies. I didn't realize they were going to. My apologies. I feel terrible. I've let you down. Mistakes have happened.
Because your handwriting's
All right. So we've already talked about power. Oh, the other thing I'm going to mention about power, and this actually works very similarly with the energy thing from last chapters. There are other equations for power. This is the main one to understand. Let's keep it right now. So Ohm's law is this. As a matter of fact, you're going to stop seeing me put the delta V on voltage. It is still technically voltage. It's still potential difference, but we don't use potential mostly in this chapter, except for some concepts, which we'll discuss a little bit later. So that being said, Ohm's law is usually written as V equals IR. If you've seen that before, Ver. Ohm's law is Ver, but it originally comes as resistance to the definition of voltage, current, blah, blah, blah. Okay? Power is voltage times current, or current times voltage. PIV. Yeah, absolutely.
Wait, what is that?
That's power. Because this was joules per coulomb, and that's coulombs per second. That is the amount of energy per child. I went back. I have a hard time leaving the analogy. I'm sorry. The joules per children. So if you want more joules, you need more children. And if you want more energy in a certain amount of time, you need more children in a certain amount of time. All right. So hopefully we're understanding that equation. Now, this is something similar I did last chapter. If you feel confused by the next two equations that I'm about to create for you, please understand these are all you need. Okay? What is the only two things you can change in a circuit? Can you go to like a circuit and just go, I'm going to change power, like by itself? No. What could you change? The battery. Therefore, you change what? Voltage. By changing the battery, you change voltage. What else could you control? Resistance. Now, technically, length of wires, you're right there in the same type of conversation. As a matter of fact, I'll show you some resistors probably tomorrow that are literally lengths of wire. that you just control how much the length of wire is, and therefore they're the easiest way to vary how much resistance is in a particular setup, but ultimately change the resistance, change what resistor is specifically there in that particular case. That being said, I gave you an example yesterday. I said, hey, the power company or the light bulb company wants to make a 60-watt light bulb. They can't actually make it 60 watts. They just make it with the assumption that the voltage is what?
120.
20, because that's what it is here in America, always in those outlets, right? They don't expect you to plug it into a 1.5 volt battery. As a matter of fact, the light bulbs that you saw in the lab yesterday that I gave you are only made for 1.5 volts. Change the voltage much past them, that's when they break, and that's when I get irritated because people are like, my stuff's broken. It actually is. So, really, the only things you can control are those things right there, right? So, that being said, what you could do is you could take this and do some substitution. If V is equal to IR, then power is equal to I times IR. Or power is equal to, oops, not resistance, dummy, power. Power is equal to I squared times R. When is this helpful? This is going to be specifically helpful when you know the resistance has stayed the same and the current has changed by a certain amount. I say I double the current. What effect should that have on power? Well, you can see here that if the resistance stays the same and the voltage doubled, then power should go up by 4. Now, you could get that exact same line of logic by looking at these two equations, because if my resistance has stayed the same and I want my current to double, what do I have to do? I have to double the voltage. And then if you take both of those just doubled and show them right here, if both of those just doubled, I have twice as many kids rolling down the hill because I have a hill that's twice as big, right? 2, 2, that means power just went up by 4. So these are kind of like, these are the main equations. I'll put those in boxes. These are like sub-equations that you can also use. Well, that's one of them. The other one is change this guy instead to I equals V over R and substitute it in as well, and you get power is equal to V over R times V. And once again, you get a new equation that's not really a new equation. Power is equal to V squared over R, and it's helpful. Specifically, this one is particularly helpful because the only things you can control are voltage and resistance. So if I say to you, I double the voltage, I keep resistance the same, what should happen to power? It should go up by 4. Yes, quadruple. I double the voltage, and I double the resistance.
Oh wait,
It stays the
2
same.
times 2.
Should go by 2. Why would voltage matter more? Well, let's see. I said I double the resistance and I double voltage. Well, if you come up here, in that math equation, yes, but if you come back up here to understand why, if I doubled voltage and doubled resistance, what effect would that have on current?
Oh wait, hold on.
Current would stay the same, yes? But in this equation, current stayed the same, but what did the voltage do? Doubled. So what effect should that have on power? It should still double. You're definitely getting problems like this almost identically on the test. So need more help? We feel good.
Wait, can you say it again?
Sure. I'll give you one more. Let's just do this in your. Try to put all of them up there at a time.
Shut up, Ava. Not you, it's Jackson.
I want to triple power. And for whatever reason, I want to use a battery that's twice as big. How can I do that? I don't know the answer yet, so I should probably figure it out. I want to triple power, and I want to use a battery that's twice as big.
So you
How am I
want
going to do that?
when you say you want a battery that's twice as big, you mean you want a double voltage?
Yes.
Okay, great. And then what are we trying to find?
I want to. I said, how are you going to do that?
Okay.
So I want to double voltage. I want to use a battery that's twice as big. So instead of my 1.5 volts, I want to use 3 volts. And I want to triple power. How can I pull that off?
Oh,
Let's start off with the easy thing. What should you be looking, what variable should you be looking at here? I said I want triple power, and I'm going to use a battery that's twice as big. What measurement should you, I asked what should you do? Well, what are the only two things you can control? Resistance and voltage. Well, I already told you the voltage is going to double, so what's your only other way of changing these numbers then? Changing the resistance. So you should be looking at what effect this has on resistance in order to triple power, make the voltage twice as big. What is it? Just say that that is the correct answer, except you didn't quite say it right.
You should multiply the resistance.
In other words, you should use a resistor that is 4/3 as big as what you just had.
I did it!
Does that make sense? All you should have done to do that is this right here. That doubles, so 4/3. Does that make sense? Okay. I'll tell you right now, there's at least 2 or 3 problems like this on the test, and they usually come across like, hey, which one of the following scenarios will double power? Or which one will quadruple power? And it'll give you a combination of various things, and you should be able to do this pretty easily. I believe that's it. That's definitely not as fast as I told you. Oh, I do need to talk about superconductors super fast. Okay, superconductors. So superconductors are not something that you and I will have to deal with in here, okay? Because superconductors have an interesting relationship. You saw on the previous slides that as temperature goes up, what happens to resistance?
It moves up.
What's that?
It goes up. Temperature goes up, resistance.
Yes. So if you reverse that process, if we make it colder and colder and colder and colder and colder, that would mean that resistance goes down. This is why supercomputers are usually super cool. And why, if you have your laptop or your computer on in a room and it's stupid hot in that room in the summer, it sucks. It is not going to work nearly as well. It's also why these guys right here have temperature gauges inside of them, that if they get above a particular temperature, they go, nope, I'm too hot. I'm not doing anything. Wait till I cool down. They're also trying to make sure that they prevent that short circuit situation we were discussing earlier, so they don't melt and obviously then have to break and that type of deal. But specifically, if they are colder, they will work better. As a matter of fact, here's a quick aside. Specifically, if you're going to want to, I mean, you're in the later part of the year, it's going to get winter, you're going to want to be in your bed doom scrolling at some point in time. So just as a heads up, if you use a case on your phone, that's fine. If you ever are using a case on your phone and you find that it's getting particularly warm and not working very well, specifically in your bed and you're not worrying about it falling, pop that bad boy off, because a cell phone's heatsink, I forgot this blue. Anyway, a cell phone's heatsink is the case. And so when you wrap it in a blanket, it inherently will in fact become warmer, and therefore your cell phone will suck a little bit more. So specifically also when you're trying to charge it, it's also going to get warmer because it's flowing more current through that particular system. So if you're sitting in bed and you're not worrying about breaking it, and you find that you're charging it and it's just not working very well, pop your cell phone case off so you can mess around with it. Just make sure and obviously pop the cell phone case back on later so that you don't go and break it and all that sort of fun jazz like I do. All right, back to the conductor thing. So we work our way back down, we get resistances that are smaller and smaller and smaller and smaller and smaller. The interesting thing that they've found is this graph right here, that at a particular temperature, and please note, by the way, the scale, they don't present this very well. That's 4, that's 4.2, that's 4.4 Kelvin. All right, so cold. All right, so you're dropping. They found that this guy right here actually takes a steep drop off at a particular point, and this is what they call a critical temperature. A critical temperature is for a material where basically at this temperature, there's 0 resistance. Now at 0 resistance, if you just get current going, do you need a battery anymore? No. Now a battery's not inherently helpful because now you just got a bunch of kids running around the top of the hill. Okay? The kids are running around the top of the hill, and you go, that's not particularly helpful. They're not getting any energy out of the situation. They can't power anything with that. But what we're going to find in the coming chapters of magnetism is actually the fact that they are moving has a major effect on magnetism. So cooling things down to a particular spot can actually turn the current itself into a magnet, and superconductors can actually create what's known as, I think a lot of times called quantum levitation. And if you get something cold enough, essentially you can turn it into a magnet that holds stuff in place in that particular way. So a superconductor is a material that if you drop it to a particular temperature has no resistance, and this is more application long term. This right here is a page of what is the critical temperature of most materials. And notice that all of them are freaking in Kelvin. So all of like your zinc, aluminum, what I can't remember what that is, mercury, lead, neodymium, not neodymium, I can't remember what that is off the top of my head either. But the best you can do is like 18, okay? You get these crazy chains down here that they're working on. The best we've done so far is 134, which sounds great, relative. But I want to remind you that 134 Kelvin is still, yeah, you get it. Negative what, 240, no, 236, 239, negative 239 Celsius. So I wouldn't want to hang out there. But they are trying to work in that particular area. All right, that's all I got. I'm done with chapter 17. We'll do a lab tomorrow. Bye-bye.